Hello, welcome to the latest episode of Data Unchained. I'm your host, Molly Presley, and we're broadcasting today from our Supercomputing edition in St. Louis, live from the trade show floor. This week, we've been talking a lot about data management and some of the global data access challenges on the podcasts that we've been reporting. But this one's going to be all about performance.
Heck yeah.
We're at Supercomputing, and we do like performance. So without further ado, let me introduce today's guest. John Flynn is the first time on Data Unchained, and he is responsible for the performance labs at Hammerspace. But before we jump into that, tell us a little bit about your background.
Yeah, sure. I have a bachelor's degree in programming, but have always applied that to scripting and driving the most performance out of whatever I can get my hands on hardware-wise. That said, aside from my obsession with performance, I actually dabble in restoration, modification, and repair of retro gaming consoles, which I find to be a lot of fun, but since I started here at Hammerspace, I haven't had as much time for it.
Very cool. So at Hammerspace, you are focused on performance. Talk a little bit about the performance labs and what your kind of scope is there.
Yeah, so I'm technically the director of applied systems, right? I have a group that works with me, a couple field CTOs focused on cloud and partnerships, as well as another performance guru. We run our own performance lab in our space, which is dual 400 gigabit Ethernet, a good number of servers based on Xeon Gen 5.
Wait, I have to ask you, Ethernet, aren't you running InfiniBand? Isn't that what you need for performance?
Well, we run RDMA over converged Ethernet.
Okay.
Right? So while RDMA is incredibly beneficial, it's not necessary,
okay.
Right? So Ethernet, especially with NConnect and the NFS protocol, is more than capable of saturating high-performance networking. That being said, we do support InfiniBand and RDMA over InfiniBand, which is part of our subject today, part of what we're doing.
Perfect. Was there anything else about the lab architecture before I interrupted you so rudely?
We have enough to be able to do IO500, 10-node challenge as the need arises, and we're actually expanding. So we'll have, a good number of servers in the 50, 40 range that we're going to, the new set coming in will be dedicated to additional performance enhancements, and we're going to be dedicating a lot, in some of the older hardware, to remote POCs, the ability for our customers to log in and kick the tires on a well-known, well-understood performance test rig versus, always deploying in a remote environment.
So we launched the general availability version of Hammerspace about 3.5 years ago.
Yeah.
And was pretty focused on our data orchestration capabilities at the time. And I think one of the things that in this space people think is, okay, if you're moving data around, whether it's orchestrating or data management, you're by nature going to be very slow. Like, this is just kind of one of those legacy things that's in people's brains. Now we hired John and your team to really exercise and show the performance capabilities of this technology and start to really prove, is it slow or is it medium, or can it maybe even be used in HPC? And so I think that was an interesting change in our focus as a company as you came on.
So I think what's interesting, part of what brought me to Hammerspace 2 years ago at this point was the underlying technology of parallel NFS or PNFS. When we look at that core fundamental building block that we work on, that our data orchestration works across, in its heart, it's a parallel file system. And so part of my initial drive when I first started was to look at, okay, let's really test the data path. We have a performance engineering team, and they look at the metadata path. Now, obviously, I look at both eventually.
Sure.
But the thing that I wanted to verify was the data path and how it performed. And I'll say that there was work that was needed. And part of that work is how we got here today, and the ability to bypass the page cache or the buffer system on an NFS server and do direct IO or ODirect.
Okay.
And that's a big part of this new release.
Okay, cool. So you came on, got to know the product a little bit, and the first benchmark you ran was an MLPerf, when the MLPerf for storage benchmark came out. Maybe talk a little bit about that architecture. I think it's a little bit more how people generally think about benchmark architectures looking like with external storage.
Yes, yeah. So there's a lot you can do with basic synthetic test tools like FIO, right?
Sure.
And you can really test out the system to see that it's performing as you would expect. But what's more important, and this is partially what my team does, is it looks at the performance of your storage subsystem from the perspective of the application. And so when we look at these industry standard benchmarks like MLPerf, they are meant to emulate what is done in actuality on a training cluster, for example. So the first MLPerf that we submitted was actually done by another team member, and that was based in the cloud, right? It had great performance. That was the MLPerf 1.0. And then we followed that one up with MLPerf 2.0, and that was done on bare metal in the newly established performance lab.
And I think the thing that we proved in the first one was, as a parallel file system, this is HPC caliber. We all know the top 3 or 4 parallel file systems in this space. And the results were sitting in that area. Parts of the workload were higher, parts were a little bit lower, but it's a solid HPC file system.
That's exactly right, especially being able to demonstrate it in the cloud so easily, right? That put a first, dot on the map from an industry standard benchmark perspective of, yes, it does qualify as a world-class parallel file system. What really takes it from there is our initial submission to the IO500, which was done by Hammerspace for ISC25. And in that particular one, that's where we actually showed the world-class bandwidth and performance that the file system can provide.
Right.
And did it in such a way that it scored quite well on the 10-node research list.
So that was really demonstrating in that research list kind of a scratch use case. Maybe talk just a little bit about that architecture.
Yeah, sure. And that's a big difference between that submission and this new submission. In the initial submission, we had a single Anvil metadata server. In Lustre parlance, you would call it an MDS, right? And because we only had a single, we couldn't actually submit for the production list because it was technically a scratch file system. If I lost my Anvil, my file system was down. My data was down.
Right. And that's what you want in Scratch. I mean, it needs to be low cost, super fast. If you have to start over the job, not great, but it's okay.
Exactly.
But let's fast forward to what we're doing here this week at Supercomputing 25. So you embarked on the production 10-node challenge.
Yes, we did. And we actually did this in conjunction with our partner, Samsung. They graciously invited us into their lab and said, we want to do some benchmarking together. We want to beat your number, was really what they said. And they actually went through the effort of upgrading their network to 400 gigabit InfiniBand.
Okay.
Hence the comment. And with the 400 gigabit InfiniBand, that actually brought their servers up to par with what we have in our lab. Dual 400 gigabit Ethernet versus dual 400 gigabit InfiniBand. The other thing they did was they did all of this benchmarking on their new PM1753, which is Gen 5 NVMe fantastic drive, and it actually proved out very well in this test.
Okay. So there were some other changes made since ISC. Maybe talk through the production challenge. There's a few different scores you get, right? And the hard reads, hard writes, metadata. Maybe talk through a little bit about the benchmark and what changes we made to optimize.
Yeah, as we look at the new score compared to the old, you'll see some noticeable differences. The first one is we implemented a HA failover Anvil pair. So we wanted to get this one to the production list. So the first thing we had to do was harden the metadata to be able to withstand a failure, right? So with our standard approach of metadata today, you have an active-passive Anvil pair, and that allows you to fail over in the event of a server failure. Now, because it synchronously replicates the metadata as it's created, it does have an impact on metadata performance. And so what's interesting is even though our new score is higher all the way around, if you look at subsequent metadata test scores, you may notice that some are higher and some are lower. That's in part due to progression of the stack, meaning that the file system from the metadata server perspective is performing better in some cases. And in the cases where it's lower, it's simply because the active-passive failover Anvil pair has impacted the performance negatively in some ways. So that's really the first key change that really allows us to apply for the production list.
Okay.
Now, as we move on a little bit further, the next key piece that you'll notice, and really the key contributor to the increase in performance, is the IOR hard read and the IOR hard write. If you don't know, the IO500 does a composite score using a geometric mean of the IOR test and a geometric mean of the metadata test, and then you do a geometric mean of both. But that's a bit aside from the point. The key component here is if you have any score that's below 1, it can greatly impact the geometric mean of the test.
Sure.
So in one area, the IOR hard write, we were able to bring in some advancements in the upstream Linux kernel, specifically around NFS and XFS, that helped to improve the locking mechanisms during IOR hard write. Now, this is locking mechanisms at the XFS level, and that provided about a 30% increase in performance just from the IOR hard write perspective. That didn't come all the way through to the final benchmark because we made one other change that directly impacted IOR hard read.
Okay.
That change is how we implemented Hammerspace's unique ability to apply objectives at a per file level to do specific items with the data. So, whether it's moving from tier to tier or performing some other action, in this case, we applied an objective that made 10 instances of the file. Now, this wasn't after the fact. We actually used client-side mirroring in the parallel NFS space in order to create 10 different instances on all of the back-end servers. This does have a direct impact on IOR hard write. And so where we could have scored a 1.3 on the hard write, it dropped to about 1.15 because it is doing this synchronously during IOR hard write, meaning it's writing to all 10 instances simultaneously in order to later take advantage of it in the IOR hard read. So in IOR hard read, now our score is based on a PPN of 56, or processes per node. So that's a total with a 10-node challenge of 560 processes. So in the IOR hard read, what we did at ISC earlier this year was all 560 processes hit one instance of the file on one volume in the Hammerspace file system. And so that scored well. It was 12 to 14 gigabytes a second. But with 10 different instances of the same file, all written synchronously, all completed during IOR hard write, during IOR hard read, when each client opened the file, it got a different instance. So 10 clients hitting 10 different instances of the file on the back end.
Yeah, that's a beautiful setup.
Instead of 560 threads against one instance of the file, it increased the performance because it was 56 threads per instance, effectively taking that score up into the 98 gigabytes a second range. And that is a substantial improvement over the previous result. The last thing you might notice is that the bandwidth score, the IOR hard or the IOR easy write and read, in this case, due to progression of the stack, especially additional work around the new product or the new feature that we've contributed upstream called NFSd Direct. Mm-hmm. That concept of direct I/O versus buffered. Due to further enhancements there, the sustained score increased on those as well. And so that's kind of the aggregate. A little bit of decrease on metadata, a little bit of increase on the easy, IOR easy, and a massive increase on the IOR hard writes and reads. So
we haven't talked a lot about Tier 0, and to be honest, there's been some rumblings in the community of like, wow, this is almost an unfair advantage to Hammerspace that we can do this, right?
Yeah, no, exactly.
And this particular benchmark, the IO500 10-node challenge, you can't use it. It's not the design of that benchmark, right?
Well, technically we could, but from a design decision, it didn't make a lot of sense in this particular case, simply because the dedication of the clients to do the compute portion made more sense in this particular case to keep it disaggregated. Now, that being said, it's probably would perform quite well, and it's just a matter of time to test.
Okay, fair enough. But you have done MLPerf with Tier 0, right?
Yes, absolutely, yeah.
So let's talk just a little bit about that, because that's really the epitome of the fastest, lowest latency
absolutely
solution, and we can't leave supercomputing without talking about that.
So tier 0, the concept of taking your NVMe devices local to the GPU or the compute node and effectively adding it to an NFS server, exporting it, and adding it to the parallel NFS file system is amazing from the perspective of simply economies of scale, right? You've got cost, you've got performance, and you've got economies of scale performance, meaning per node, a tier 0 node is faster or as fast as a tier 1 node, and then I have many, many more compute nodes typically than I do storage nodes. So I have more, and they're as performant as. That's key number 1, right? Last one is it's a sunk cost. I already bought them, so the storage is actually quite cheap there. So really, it's quite an attractive area to do storage, but it comes with its own management concerns.
Yes,
right?
Legacy mythology jumps in a bit here too.
Exactly.
Actually, not mythology. It's just you needed some tooling to fix it, right?
You have to follow some good guide rails to ensure that your data is safe. And whether that means it's a primary storage area or it's a scratch space, right? There's multiple ways of looking at it. But let's jump into that MLPerf. MLPerf 2.0, we decided to do it as a tier 0 implementation. We effectively created 5 copies of the data using client-side mirroring and Hammerspace objectives again to generate the data across all nodes involved during the tier 0 test. That effectively gave us 100% locality. So whenever we performed a read, we were reading from the local NVMe. And that provided a lower latency, a higher sustained bandwidth and throughput number than you could possibly do over the network. Now, to be fair, my lab has 800 gigabit networking. So technically, it became borderline on whether or not this tier 0 implementation was much faster than the tier 1. But generally, you don't have 800 gigabit to everything, right?
Right. That's fair.
And so in the end, the local NVMe provided me enough performance to sustain 28 H100s. Now, you're not going to find a GPU server out there that has 28 GPUs in it. Of course not. At least today. You could argue an NVL72 has 72, but technically that's 18 different compute nodes.
Exactly.
So, but that gave us the advantage of essentially reading locally. Now, that takes advantage of a few different features that Hammerspace has made available to the industry. One is we've checked in a technology called Local I/O into the upstream NFS client. Local I/O allows the client to talk to the server and realize, oh, I'm the same person, I'm the same server. So it will allow the client to directly communicate with the XFS file system, bypassing the networking stack and the NFS server stack, effectively increasing your bandwidth and decreasing your latency because you are getting rid of a lot of the middlemen as it goes. The second piece to it comes in at our metadata server. Our metadata server will recognize when a client that's requesting a file is also a server. So if that client happens to have an instance of the file, it will serve out a layout, an NFS layout, to the client that is its own instance.
Which is really cool.
It synergizes.
Yes.
It allows the server and the client to now negotiate local I/O. And so it was a two-part on that MLPerf. One was local I/O, and then the other one was the data replication using objectives, and then, of course, the affinitization that served out the appropriate instance of the file.
That's beautiful. So driving this all into the standards makes it available in any build of Linux. So whether that's your GPU server, your supercomputer, whatever you're running Linux on, gets to take advantage of this. And if it happens to have some available local storage, take advantage of it, save some money, go super fast, right?
Exactly. And again, I'll emphasize that the work done by our kernel engineers, Mike Snitzer, for example, is key to the performance we got in both IO500s, both earlier this year and now. And that's that technology, NFSd Direct. It is the ability, again, to bypass your page cache or your memory management subsystem using ODirect. So when an I/O is aligned, it will get flushed via a DMA directly to NVMe, or it'll be read directly from NVMe and put directly out onto the network. If it's unaligned, this is the interesting part, is, well, my I/Os will fail with ODirect if it's not aligned. Well, we flush the center of the I/O, the aligned portion, and then we put the unaligned head and tail through the buffered path. and that was integral to the IOR hard write, because keeping those in the buffer allows you to avoid read modify writes. Not all of them, but some of them, because the last read modify write was for a block that is used by one of the other threads who's doing the similar action. And so it allows the synergy and allows you to maintain performance. So anyhow, these enhancements, NFSd direct and NFS direct, which is client-side stuff, which will be potentially used to great effect in further MLPerf testing, those are going to be going into the kernel in the upstream soon, right? We missed the last merge window. There was a lot of negotiation and proving these things out, right? We're not the maintainers of the NFS server. Our CTO is one of the co-maintainers for the NFS client, and in a way that makes it harder.
Right, he has to even play more conservatively in some ways in the community.
Exactly, and so we have to prove both to the server and the client maintainers that these benefit all, not just ourselves, right? And with that, it was a full study on the memory management subsystem, proving things out that once these things become contentious, once you put so much pressure on the memory management subsystem, that it impacts your performance. And with this, I can demonstrate with FIO a sustained bandwidth of 98 gigabytes a second. That's 98% of my pipe, right? Using FIO for reads and writes. Writes depends on my NVMe, and I can show a sustained 71 gigabytes a second to my NVMe. If I had more in there, I could probably push that same 98. So no, these enhancements are integral to the future of NFS, and it's not just for us.
Yeah, absolutely. So I was at the HPC Legends ceremony today, which was Tabor Communications awarding the top 35 contributors to HPC, some absolute legends. And two of them were focused on driving standards into supercomputing. One was more on the networking side, and one was the one who proved that you could run a supercomputer on Linux. And this is really the path that this industry has taken, is you can go towards standards, you can drive down costs, you can do more research, more helping humankind on a lower budget, and this is the next step, right?
Well, absolutely. I mean, if you think about the nightmare of taking a traditional parallel file system in the space and keeping your system functional, kernel upgrades, you got to rebuild so much. Like the thick client.
And not everyone has a kernel engineer on staff.
That's fair. But the thick client that most parallel file systems require, they require direct alignment with the kernel a lot of the time. And you can't just load things up. You have to make sure that your kernel and your software stack match, and when you upgrade, you have to upgrade them in lockstep. There's systems to make this easy, but it's more complicated, and it isn't always easy, right? And so by having it built into the open standard, having it built into the kernel, your upgrade just comes with your new kernel, right?
Exactly.
Now, it's not always that nice. Sometimes regressions happen, but generally speaking, when you get a new kernel,
pretty well vetted.
You get new features, right? And that's why the kernel maintainers are always leery of simply accepting a patch. They want to test it. They want to know why it needs to go in, and that's why this is so exciting. And all of this is actually built into our 5.2 product line,
which we just announced this week, just a couple days ago.
Exactly.
Very
cool.
Super
exciting.
It is. Certainly, Hammerspace customers or prospects who are looking in this space, if you don't have a performance engineer, you can definitely understand the value of one, and we make John and his team available to our customers as well for some of these little tweaks that make a huge difference as well.
Yeah, I'm involved in so many POCs. It's so much fun, right?
Yes.
To be able to make a system sing, it's great.
It is. It's very cool. Well, Jonathan, thank you for jumping on to the podcast
worries.
And for all your hard work, and congratulations again.
Thank you much.
Thanks for listening to Data Unchained, powered by Hammerspace. To learn more, visit hammerspace.com. If you have a guest you would like to hear on the show, email me at molly@hammerspace.com.